Hey, all right, guys. So welcome back to another episode of Freud Games. I'm using the word episode because usually is kind of like an episode. So in the last class slash episode, what we did was what was that? So we take normal curve, right? So if you remember, normal curve and calculations. So it is based on the percentage of area under a particular limit, and we also talked about percentiles and stuff, right? So at the end of the episode, we saw that like our characters are stuck with a decision, two paths. Which one would they choose, right? So that is what you guys are going to do. So I'm going to be presenting a few, what do you call it, options for you guys to choose. So you have to click on the text that you think is right, and you'll get feedback whether it's correct or not. So there may be a few calculations, but it should not be that difficult. Okay. So are you guys ready? So can we go forward? It'll be kind of like a cognitive check for whatever you have seen in the previous class. Ready? Or no, you guys don't remember what you saw in the previous class? Okay. So as usual, you guys have this one will need more time. So you guys have 3 minutes of time. Just the time up. All right. So before we go in, if this is your first time joining, my name is Rodrick, and so you may be part of the WhatsApp group. So yeah, if you're from YouTube, so this may be your first time too. Anyway, so we have this interactive PPT called Freud Games. So you can interact with the slides if you join from Teams. But if you are from YouTube, obviously you can only see it from stream or the recorded video. All right, so you guys have 3 minutes of time and you can start solving, hopefully. Oh, wait, sorry, my bad. Yeah. What you have to do is choose the right direction. You have to click on the text that is shown here, right? So after you guys have completed, and of course, I'll explain why this is right or why this is okay. So just hit a thumbs up if you have completed. Oh, that was quick. Okay. So this is based on the normal curve. The normal curve was actually discovered by the French mathematician Abraham de Moivre when he made the formula for the normal curve. But it was later rediscovered by Carl Friedrich, and it was called the normal law of errors because he plotted errors on measurements and it was normally distributed. So it is not normal law of data, but it is normal law of errors, and it was discovered in 1733. Right? So in a normal curve, we know it is symmetric and it is mesokurtic. So the kurtosis is 3, but skewness is 0. So it is not kurtosis that is 0, but skewness that it is 0. Right? So if we have a negatively skewed distribution, mode is the largest value. All right. So let me do something here for you. The camera can be switched off because it's just lags. So a negatively skewed means you have a tail on the negative side, which is the left side. Right. So mode is always the one that is peaked. So mean is usually on the side of the tail, and median is between mode and mean all the time. Okay. So in a negatively skewed distribution, obviously, mode seems to be the highest or largest. Okay. So let's erase these stuff. So this may be difficult for an IQ test with mean of 100 and SD of 16. The 97.5 percentile is actually 132. So I'm not going to explain this because we have already did this in the previous class. It'll just be too redundant. So you guys go there and check it out. The normal curve can be used as a model for all distributions of nature is false. It is best used as a model for sampling distribution. Okay, so we talked about what is sampling distribution. So uh, this is what you guys were up to, and so did our characters. So every time they choose, they apparently have even more choices. Of course, choosing things over and over is taxing. So what they do is they simply say, what if we keep just taking one option? There are only two options. What if we keep taking left, 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 left? So even then, we may end up with 50% of the correct answers, right? So that is their hypothesis. So how are they going to test it out? You'll have to learn a few, you know, metrics or a few details on hypothesis testing. Okay. So has anyone already completed or completely read about hypothesis testing, standard central limit theory, or even maybe errors in hypothesis testing? So if you already know it by heart, maybe put in the chat. Anyone? Okay, I guess you're all new to this. Fine. So as usual, we'll have 1 minute to unlock the next slide. The next slide will be about research design in general. What is a major purpose of research design? And then we'll go to hypothesis and maybe research problem, research questions as well, right? So this is going to be the 5th episode, research design, problems, and hypothesis testing. You guys have 1 minute to unlock this slide. You can just click on the block and it will show you options. Choose the right one. So you guys have 1 minute. Thirty seconds are up. So you guys have 30 seconds more. Okay, so someone finished under 50 seconds. That's nice. So research design has two basic purposes as we see first. One is to get answers to your questions. Okay. So in the example of our characters, they want to know if we keep taking left, will we end up with 50% of the correct answers? Logically, yes. But are they going to test it out? And are they actually going to get that? Right? So the second purpose is to control variance. So we know the formula of variance. So it is sum of deviation squared divided by total number of samples that you have, right? So variance also means how it differs from the mean and in a way each other also, but that does not actually variance, but how it differs from the mean is what is variance, right? So we are supposed to control variance so that we can make conclusions. So research design is your instructions to be able to control variance so that you can conclude something. So we have various other research designs like experimental, they have a lot of research designs like experimental design or correlation, or maybe you just have an exposed factor design. So all of them have these key principles. Okay? So the statistical principle behind controlling variance is that you have to maximize the variance that you really want, this systematic variance. All right. So it could be independent variable. Okay, so dependent variable. So these do vary in a predictable manner, right? So at least IV, it has to vary, and DV you check whether it varies or not. So DV is dependent variable. So that is what you mean by maximizing statistical or variance. So whatever independent variable you have should be varying most maximum possible range, right? So you cannot only have manipulation of IQ between 101 and 100. It doesn't vary much. So you should have IQ scores which go from almost zero, almost the top of that particular scale. Let's say maybe 145 or something. So that you can make proper correlation. Right? Second is you have to control extraneous systematic variance. So extraneous systematic variance is anything that is extra but varies systematically. Right? So we call this particular type of variable. So what variable is extraneous but varies systematically? Any thoughts? Always discuss this. It's called conform. When it is unsystematic and you do not know what it is, so it will be still an extraneous variable. But once you know it is varying systematically, it becomes a confounding variable. And you're supposed to minimize error variance. Right? So error could be in measurement, could be in sampling, or could be just conclusion. So there are so many sources of error. So we'll not go too much into this because our aim is hypothesis testing. Okay. So you guys have just 30 seconds for unlocking the next slide. Oh, okay. So a few of those slides are kind of unlocked because of adjustment of size. It's okay. So we'll just discuss this then. All right. So what is a research problem and what is a hypothesis or maybe research question is what we're going to look at for now. So let me explain the slide because blocks are out of the words. Anyway, so a research problem is something you decide way before you conduct your study. It requires planning, a priori planning. A priori meaning even before. Okay. So the first step is in any research is identifying the research problem. But how is it different from a hypothesis? So hypothesis is usually very specific, testable, declarative statement. Research problem is usually kind of a vague question about your variables, maybe relationship of variables, difference or presence or absence of variables. So it could be a lot of. The research problem is a very vague question, not a specific question. Then it will become a research question. So research question and research problem are actually different. Research question is very specific, like hypothesis, but research problem is a bit vague. It is almost like research area. Okay. So if you want to say, if you are studying clinical psychologists and their mental health, so you can maybe ask a research problem. Are clinical psychologists' mental health well tested? Or it could be even more vague. So clinical psychologists, they take care of their mental health. It's not exactly testable, but it's still a question, kind of an area. Okay. So Kerlinger had talked about research problem. He says the scientist usually experiences some sort of an obstacle or understanding, and you get a lot of interest in something. That is what is your research problem. Usually it is a question format. Okay. So next we have hypothesis or questions. So again, you guys have 30 seconds. It should be a lot. So could you just let me know when you have completed? There's a question in the chat. Okay, I'll come to that. Oh, just two, so it should be pretty easy. So research hypothesis, as I said, is something that is declarative. All right. So it is also a predictive statement. So we make predictions. So we make tentative solutions or assumptions about maybe relationship between variables or difference of means or scores of two groups on the same variable. Right? Research question, on the other hand, is different from research hypothesis. Is also different from research problem. Okay. For example, if research hypothesis is like IQ is correlated with academic performance, or you could say GPA. All right. So this is a predictive statement. It's significantly correlated. You could even say statistically at this particular significance level and stuff. That is a research hypothesis. But research question is made in a interrogative format. Is IQ correlated with whatever you're studying? GPA or creativity or maybe happiness in life or something like that, right? So it's phrased in a question format. It's pretty easy, but it is still very much guessable or highly specific. Right. So what do you guys think? Do IQ predict happiness, or people with extremely high IQ feels extremely sad in most of their life? First slide. I'm not sure if we can go back, but anyway. So during break we can. If there's any doubt in that, you just like. So what are the various types of hypothesis or question? So you have heard null hypothesis, alternate hypothesis. Apart from that, yeah, I should have highlighted this, but we have a minute to unlock this. Then I'll link to you. So you can see already there are 4 types. Okay? You guys have 1 minute and let me know when you have unlocked. You have 30 seconds more. Sorry, 20 seconds more. My bad, my bad, my bad. Yeah, back to this. I hope it didn't clear all the things. So yeah, we can have a little bit more time. All right, cool. So we saw what is hypothesis or even questions, right? So we usually broadly classify them in 3 categories, but combination, not combination of these 3, but more like multivariate type of either of this. Okay? So the first one is difference hypothesis. So we've been talking about experiments in the previous classes. Even now, we just vaguely brought it up. In experiments, what do? You have at least 2: an experimental group and a control group. Okay? So you compare the scores on 2 groups on a single variable, right? So that is what is called a difference hypothesis. So it will be framed like the experimental group, which got CBT, has higher scores on coping compared to the control group who did not get CBT. Right. So this, of course, it's not a very statistically framed hypothesis, but still, we'll talk about those statistical hypotheses and stuff in the next slide. So here you need one dependent variable, okay, and at least 2 groups. So one will be obviously experimental group which gets treatment, and the second will be control group. So this is in an experiment. They can also have such things in exposed factors, one which already had the exposure and a group which did not have the exposure, right? So ideally we'll be testing mean differences. If we have, a lot of parametric statistics, and if you have a normal distribution, and also the assumptions of the parametric statistics are met. We'll talk about parametric and non-parametric statistics later. Okay. So your hypothesis here, usually what we call as the null hypothesis, is to demonstrate there is no significant difference between the two groups that we are comparing. So what test we use? We can use t-test if it is not normally distributed, if it's like slightly leptococcus, or z-test if adequate sample size and it is normally distributed, which is kind of the same logic. But if you have several groups, more than two, we can go with something called ANOVA. We are still testing mean differences. On the non-parametric side, we can have median test, right? So you have Mann-Whitney U test, you have Kolmogorov-Smirnov test. So there are like various non-parametric versions. Right. So any doubts with difference hypothesis? You need at least one single dependent variable, or you need one dependent variable, because if you have multiple, it'll become something else. We'll talk about that. And you need at least two groups. Okay. But on the other hand, when you talk about associational or relationship-based hypothesis, you need two variables that will be measured on the same group. Okay, you don't need two groups, but you need two variables. For example, as we are talking about IQ and maybe happiness or GPA or something. So you cannot compare IQ of, let's say, class 10, happiness of class 8. So you cannot do that. You need the same group on two different variables. Let's say variable A and B, or something like hours of therapy and coping skills. More hours of therapy obviously may have more coping skills, right? So here you have a single group, but two variables. So we use associational inferential statistics. Here also we use inferential statistics. It's called difference inferential statistics, like t-test and all. But here we use associational, meaning relationship based. Okay. So it helps us understand how two things relate with each other, correlation or co-vary with each other. So based on this, we can also predict one variable from the other. So prediction is possible because of regression. And if we just want to know the relationship, we have something called correlation, right? So we have different types of correlation, Pearson's for parametric versions, Spearman's for non-parametric version. We also have Kendall-Tau, which is about how people rank, different data. So that is usually something we don't use, but it is also non-parametric. Then we have something called descriptive hypothesis. So here we do not use inferential statistics. Yeah, here we do not use inferential statistics at all. We use differential statistics, sorry, descriptive statistics. I use the very wrong term, differential. It is called descriptive statistics. So it is more of describing the distribution. You use mean, you use standard deviation, you can use frequencies, mode, even median stuff. So you may hypothesize that the mean will be this. Okay. But it is greater than another group or lesser than another group, right? So you may predict about prevalence of a particular disorder in a particular population. Right? So that can also become your descriptive hypothesis. You can say a particular diagnosis, maybe autism is high among males, right? Or is prevalent at so and so percentage among males, right? So that would become a descriptive hypothesis. But if you do it like autism is higher among males compared to females, then it becomes a difference hypothesis. Okay, so we just use descriptive statistics for descriptive hypothesis. Very easy, obvious. On the other hand, we have something more complex, when we have more than one independent variable, sorry, dependent variable, independent can be more even in difference, but when we have more than one dependent, which is also your outcome, there's no ink on the slide. Okay, so now it came. So when we have outcome variables and outcome variables are two or more, so then it becomes complex, right? So how do you combine them? So we use some multivariate statistics. Okay. So this is what is called a complex hypothesis. Again, it can be complex difference hypothesis where we use MANOVA. Okay. A complex association hypothesis where we use several dependent variables and predictors. So we have multiple regression in that case. And we have distributive hypothesis. So we talk about several disorders and their distribution in a particular population. That will become complex descriptive hypothesis. Okay. So MANOVA is for, let's say, a difference hypothesis that is complex. Multiple regression is again based on prediction, and for association, so it is complex association. Let me just go back. Oh god, the lag is a bit too much. Am I audible? Can you guys hear me? I'm just trying to close unnecessary tabs and stuff so that it doesn't lag for me and for people who see. So, as I was saying, we usually use multivariate analysis. We just don't add several variables. It is also multivariate. So that is one major difference in these. Any doubt questions? I hope there are no doubts or questions. Okay. So we have some more other hypothesis classifications. So these are some things you commonly hear. Okay. So there's also some things that you may not have heard, but so you guys have again 1 minute. So let's see if we can unlock this under a minute. Complex hypothesis. Okay. You guys unlock this. I explain the complex hypothesis. Right. 1 minute is kind of up. Wait. Okay. I hope you're able to unlock this one. see so the issue on the mic. So 1 minute is up. So almost like 2 minutes anyway. Other hypothesis. So this is something you'll find in color. We have substantive hypothesis, something that is still very vague. It is not as specific as we would consider a statistical hypothesis. I'll tell you what is a statistical hypothesis. A statistical hypothesis is something where you have very specific, statistically framed questions or statements, right? Not questions, statements. If you have the mean of experimental group will be significantly different from the mean of the control group at 95% confidence interval. That is more of a statistical hypothesis. You're saying of a particular group on, okay, you should also say the variable that you're measuring, right? So that will be a statistical hypothesis. But substantial hypothesis is just saying let's say the experimental group will have lower depression than the control group, or they will have higher coping skills. You do not specify on what measure. Is it central tendency, or is it just maybe some other measurement, or is it based on which rating scale? So you don't mention much there. So it is very difficult to test. So substantial hypotheses are very vague, so they are pretty difficult to test. Statistical hypotheses, on the other hand, are of statistical significance, but we talk about statistical relationships which we deduce from these hypotheses. So we test it for significance. So now is what is important for your, let's say, assertion questions and then history-based questions. You may have heard of the null hypothesis. So there is no significant relationship between this group and this group. Okay. So it was actually given by Sir Ronald Fisher, who also gave ANOVA. It is based on the principles of falsification, which Karl Popper did talk about way earlier. It was given by Ronald Fisher. The term or the way you should test it or test a null hypothesis or test a hypothesis was actually by Sir Ronald Fisher. Okay. So all your people did have alternate hypothesis and directional hypothesis and used to test them. Ronald Fisher said, if I can disprove something, that means the alternatives is true. For example, if I could not find any relationship, I cannot say that the relationship does not exist at all. But if I disprove this fact that I could not find any relationships, that means there is a relationship. Okay? So that is why it is better to go with null hypothesis and testify them, or test them, not testify them, test them. Okay? Alternate hypothesis, on the other hand, is saying there exists a relationship or there exists difference between groups. So this was supported by Neyman and Pearson, because only we have no alternate hypothesis will we be able to make several sampling distributions. So null hypothesis stays hypothesis testing is by saying this is the zero difference. Okay. So if your mean is different from this part, that means you are significantly different. Okay. But to be able to do this, to be have this different sample distributions, have an alternate hypothesis. So this was the standpoint given by Neyman and Pearson. Okay. So we'll talk about what is sample distributions. But without sample distributions, we cannot test hypothesis too. Okay. So according to Ronald Fisher's school or opinion, so you do not accept the null hypothesis. You only reject the null hypothesis. This is something you may have heard in most books and stuff, right? But according to Neyman and Pearson's thought, you can accept a null hypothesis as in until you get a alternate, until you disprove your null hypothesis. Till that point, you can keep accepting null hypothesis because that is workable according to them. Right. So these are two schools of thought regarding hypothesis testing itself. Right. So any other doubts? We'll be going back to discuss complex hypothesis. Could you let me know what exactly in complex hypothesis you had an issue and any doubts in the previous slide? Are you guys following any questions? Ready to follow? We hit a thumbs up. So, as I said, more than variables at least. More than two variables in a different hypothesis. So you're testing two groups. Instead of testing just on depression, you're testing on depression, anxiety, and stress. But there are still two groups. You could have you more dependent variables. It can become variables. So that is difference hypothesis. In a different hypothesis, test the difference experimental and control a single view. Okay, so that is you have a relationship between two variables, IQ and let's say happiness, IQ and GPA. So these are bivariate correlation, just two variables. Okay. But you can have multiple correlation also. Okay. So how do several variables together predict one? Or you can have multiple different variables combined together, which is also called a composite. We'll talk about that later when we talk about multiple regression. Suppose you have depression, anxiety, and stress as your dependent variables. Okay. So you have three different variables. So you want to know the other factor, maybe IQ, previous protective factors like social support or hours of therapy. All these together predict a combined depression, anxiety, and stress scale. So we do have a scale DASS, but I'm saying depression, anxiety, stress are three variables. You can combine them in a way that is weighted. So I'll talk about weights and all like much later. You combine the dependent variables into one single total or overall score and you correlate them and see it. That is a multiple regression analysis, which is a common association hypothesis. But if it is just a simple association hypothesis, what we would do is we just see hours of therapy and depression scores or social support and depression score. Do it separately. Okay, so that is a major difference. So a complex hypothesis is pretty difficult to say. In a given population or a sample, you want to see the prevalence, you want to see incidence, or you also want to see, let's say, demographic differences, something like that, for several disorders. So that becomes more of a complex descriptive hypothesis. Okay? Hope that clarifies things. So how are these tests related to hypothesis? So you can only do a correlation in association hypothesis. You cannot do correlation in experiment, right? So in experiment, I mean, you could try it if you have the IV in a continuous variable, but usually in an experiment you use t-test unknowns. Okay. So when we have two continuous variables or a single group, we cannot do differences. We cannot do t-test. We can only do correlation. So that is how they're related. All right. So anything in the other hypothesis? So we'll be talking about how we'll test this hypothesis. So we'll by default we go with null hypothesis. So we try to disprove the null hypothesis. If I'm able to say, if I'm able to frame it as saying CBT does not increase coping skills, it is a null hypothesis, and I can disprove it. Then I can assume, or not even assume, even like confidently conclude that CBT does increase your coping skills. So that is the approach that is given by Sir Ronald Fisher. That is what we currently do have. But we can also state the alternate hypothesis. So this slide doesn't have anything to unlock. It is just a precursor to what we will see. We need to know what is a sample, what is a population, and what is sample distributions before we go forward. Please do pay attention here because it'll be slightly confusing. Population is what you decide to study. Okay, so it's a complete group that you want to study. If you want to study people with depression who have been diagnosed with depression, so they become your population, right? So if you say I want to study depression in Indian population, so Indian people having depression becomes your inclusion criteria for your sample, but that is also your population, right? So from this population, whatever you include in your study becomes your sample. So the population's metrics in terms of what is their central tendency, mean, median, mode, and how much the scores vary between each other, it is called parameter. Okay, so we have a true mean. So for the population, there exists a true effect, which could be mean, which could be mean difference, which could be variance and things. These are true mean and true variance. And our sample that we have drawn is a possible reflection. If we have used random sampling, we will talk about that again much later in sampling methods. The sample might, I'm using the word might reflect the population or the population's parameters. So the mean, median, mode, and the variance standard deviation in a sample is called statistics. So we are concerned with statistics. We do statistical testing because most of the time we do not have access to the entire population, right? So even if you have a registry of all Indians, how do you know all Indians who are depressed? You cannot do that. So some of your population can be finite, which is like your school's uh, students. That kind of is finite. But if you talk about something more vague, it is usually infinite, right? There it is very difficult to know the actual mean or actual variance of your population. That is where sample distributions handy. Are we clear so far before we go into sample distributions? So most of the time we cannot identify a population or population's true parameters. So we can only kind of take a guess from the sample statistics about parameters. So that is where we need something called sample distribution. Everyone on board so far? If you understood, hit a thumbs up so we know we can go. So let's say the sample, I'll draw somewhere there is space. So here red can be visible. So let's say this is the population, right? So you're drawing a sample from it. So let's say you do random sampling only. So your sample is also normally distributed. Okay. So if it is from here, it is significantly different from your population's mean. You reject this usually as saying this doesn't match our population's mean. So it may not be actually from this population. So this is one way to just visually reject it. But we don't have this data. We usually do not have the full set of data of a population, right? So that is where we draw something called sampling distribution. So if we have data on our current sample, we can assume that this is drawn from the population and there are so many other possible samples that can be drawn which fit within the ideal population. So such a distribution of all possible samples is your sampling distribution. Okay, so we can again only estimate this from our current sample. So if your current sample has a range of scores from 0 to 100, let's say some end semester exam score, right? So sample can be just two. So you may have 0, 1. You may have 1, 100 also. So all possible combinations of samples within this range will be put here. That is your sampling distribution. And then we assume this sampling distribution to be our population, because we cannot directly get data on the population. Most of the time our population are infinite. So we have to get some, I would say, jugaad or some adjustments. So which is using sample distribution. So we use a sample distribution as our population, and then see where our sample actually belongs in this sampling distribution. If it is very extreme, we say our sample is significantly different. But if it is well within the mean of the sampling distribution somewhere here, then we would say our sample's mean is very similar to the proposed population. So that is how we test hypothesis. Are we clear so far before we go into the specifics? Okay, right. So now we have another standard error. So we have talked about standard deviation, we've talked about variance, but as I said, we don't know the actual true variance of your population. So we make a sampling distribution, which is something cutted from samples, range of scores and stuff, right? So standard error is also something that we use because we do not know the population's true variance or true standard deviation. Okay. So standard error is the standard deviation of our sampling distributions. We said sampling distributions are made from all possible samples that can be drawn from our population. So when you construct all possible samples along their mean, so we get a possible shape like this. So that is the sampling distribution, and we assume it is similar to the population. So exactly like that, we assume this variance or standard deviation is comparable to our population. If you already knew the standard deviation of a population, you don't have to actually do this. So this is very redundant. If we already know the standard deviation of the population, we don't have to consider standard error at all. But in most cases, or I would say in 95%, 99% cases, you will not get the population's mean or standard deviation. So we have to calculate the standard error, which is the standard deviation of the sampling distributions of a measure or any measure that we are doing. Right? Oh, sorry, I was supposed to let you guys unlock the slide. But anyway, since I started, you guys can unlock the next one or the remaining ones. So you guys unlock the remaining of this slide. You guys have 1 minute. If you have any other doubts or questions so far, you guys put in the chat. right? Okay, as I said, we can estimate the standard error of mean from only the sample because we don't have access to it. We just assume it. What we assume is that the standard deviation of the sampling distribution is the same as the population. Okay, so it is equal to that of the population. So when you have a random sampling, so it will most likely be equal. Even the sample that is from the population will be comparable. We are talking about standard deviation, not the mean score or performance. We're talking about the standard deviation or the variance of whatever sample you have drawn using random sampling methods will be comparable to the mean. So the standard deviation of your sampling distributions will also be comparable. So suppose you have so many samples in your standard deviation or in your sampling distributions. Okay. So how do we say what is the standard error? So we just divide the SD of our sample by the total number of cells we have under root. Okay. So this is one of these formulas to arrive at what is the sampling distributions standard deviation. And we assume this is very similar to that of the population because we don't have the population standard deviation, obviously. So in our test statistics, so you know how to calculate Z, right? So if you can tell me the Z score, what are the formula is? It is usually X minus X bar divided by area of what sample you are doing. So then you're calculating for a single sample. But when you are doing it for a population, we will not use Z. When we are doing it as a Z test, we'll be using the standard error under it. It will become this when we are testing a hypothesis. Okay, because let's take the example of one sample t test. So we take the example of IQ because it is very common and we already know the population's mean as well as SD. So in IQ, the population's mean is usually 100 and SD is usually around 15 in most of the IQ tests. So we don't actually have to calculate SD for the population because the population's SD is given here. In case we do not have this, we'll have to calculate it using the samples SD in this formula. So everything else here will be the same. Your samples, whatever mean you have, and the population's mean, which is 100, divided by either the given population's standard deviation, or if you don't have it, you calculate the standard error and put it under. So this is how we calculate the Z statistic, and then we see if it is significant or not. So how do we see it's significant or not? To establish something called acceptance area, level of significance, and so forth. That will be looking in the next slides. So this is all standard error of mean. Whatever we talked about is how the mean is distributed for different samples that you draw from the population. So we have two samples, and you're comparing sample B with each other, and you think that they are not equal to each other. You cannot use this method because the population, and then you have two samples. If you do the standard error, you will get two different standard errors. So what do we do in that case? So what we can do is we can get a standard error of difference of means. So we'll go into detail again when we talk about t-test, but it goes by the formula under root standard error of variable A plus standard error of variable B both squared. And then you take a square root of it. Okay. So we can similarly do a standard error for correlation coefficient, even for median, even for proportions. Okay. So this is how you get the standard error and you compute your test statistic. It can be Z, it can be T, it can be F ratio, it can be correlation, so forth, and whatever you're testing, that is this test statistic. But instead of standard deviation, in inferential statistic, you'll be using standard error. I know it's kind of a lot, but any else questions? Any doubts? Any questions? All clear? Can we move forward? I'll take a example also, so you guys can understand it much better, right? So there's the central limit theory. So you've already kind of seen this. So you guys have 30 seconds to unlock it. This is also important when we test hypothesis. Let me know after you finish unlocking this. Okay, awesome. This is 30 seconds. So the central limit theory, as I said, is where you assume when you draw a sample randomly from a population, okay, so the means of the sample will also be normally distributed. So it actually does not matter if your population was was normally distributed. So if you draw a larger sample, the more likely it will become normally distributed, because the more you draw samples using random thing, more and more scores will be around the mean, which is similar to the population, and very few scores will be extreme scores, and over time it becomes symmetrical and it is mesokurtic. Okay, so this is what central limit theorem says. The larger the sample size, the more likely your sample approaches the normal curve. And the shape of the distribution of your initial population does not matter. This is something of a debate, but central limit theory assumes this. The shape of the population does not matter whether you get a normal distribution in your sample or not. The population's distribution does not have to be normal according to central limit theory. Right? So back to hypothesis testing. All right. So yeah, you guys have another 30 seconds. After that, I'll give you an example and hopefully we'll be able to understand everything about hypothesis. There's 3 blocks here. Right, cool. So when we test hypothesis, so even if you have already calculated a statistic like Z or T, we need to know something like the area of acceptance or area of rejection, which indicates our level of significance. So level of significance is indicated by alpha. Okay. So it is the probability of error. So error here means not measurement error and stuff like that. I mean, it could be included, but it usually means chance factor. Okay. So what percentage of chance or error do we accept? Ideally, error should be minimal. Okay. So that is why convention says we should accept no more than 5% error. This is by convention. Or sometimes we could even go more stringent and have 1% error. So 0.001 is 99.9% effect, which is even more stringent than 0.1. Okay. So this is indicated by P, so which is your probability value. P means probability. So P is the probability of error. So you may have done a lot of statistical testing because of your research. So the P value that you talk about is literally your probability that whatever mean, whatever correlation, or maybe F ratio, whatever you've got is not because of error, right? So P value indicates what is the chance of getting this test statistic owing to error. So that is our P value. Ideally, it should be less than 5%, or in probability terms, we divide 5% by 100, 5 by 100, you get 0.05. So that is a P value that you should have as a limit. It should, your ideal P value in a statistic should be lesser than that. Okay. So now we'll take an example. Let me just unlock this one. All right. So the same thing. So we'll talk about one sample t-test, or if it was very big and it was normally distributed, we'll consider Z test also, right? So same thing, you have population. So this is about IQ. So you have a population whose IQ is 100 and standard deviation is 15. So you've already been given this. Okay, fine. So now let us test it at 0.05, which is acceptable alpha level, which means 5% error is what we are accepting. So here error means chance. So the thing is, if this is your population, okay, so if you take random samples from it, what you will get is most of the time your mean will fall here. So when I say 95% effect or 95% confidence interval, I mean 95% of the cases fall in this region. So I'm 95% confident that whatever I'm getting as my samples mean is in this region. So you guys may know 95% cases lie between -2 to +2 standard deviation. So this is an oversimplification, but exactly it is -1.96 to +1.96. This is just a rounded figure. Okay, so we are taking this Z score as our limit. So when I say 95% confidence, I mean 95% of cases fall in this population's distribution. So because we do not know the actual population's distribution, this can be the sampling distribution of all possible samples, right? So we take 95% of the cases as accepted. So this distribution is the distribution of our null hypothesis. Null hypothesis, right? Now, sample, right? If it falls here, outside the means you can definitely say with 95% confidence that it is not in this area. Okay, because 95% of the times the different mean scores will be possibly here. If you get a very unique and different mean which is not in this range, you are saying with 95% confidence that it doesn't belong to the population. So that is how you do this hypothesis testing. All right. So we need the Z score values at this cutoff points. So as I said, it is for a two-tailed test where you have both sides for the testing, it is minus 1.96 or plus 1.96 in terms of acceptable Z score. If your sample's Z score is anything here, then you say it is part of the same population and you do not reject the null hypothesis. Right. So let's take a numerical example. Okay, so there's a question in the chat. I'll come to that. The numerical example is, now I have drawn a sample, okay, and that sample has a mean. I'm going to put it as sample A, and that sample has a mean of 115, or let me keep it as 115 for ease of calculation. All right. So what will be the Z score of this mean compared to the mean of the population? So if you were to convert this value to Z score, what will be the Z score? Anyone? So I have drawn a sample from the population. Okay. And the sample's mean came out to be 115. Not a single person, but a sample's mean came out to be 150. So what is the Z score for this? It will be plus what? It will be plus. Okay. So as we had discussed earlier, 95% cases are between 1.96 on the negative and plus 1.96 on the other side, which is positive, right? Obviously, plus 1 will be here in the acceptance region. So if this sample was normally distributed, then, and it has the same standard deviations, we can say that it belongs to the population, and I can say this with 95% confidence. The chance of it belonging to some other population or on the rejection is very, very less, right? So that's how we come to the conclusion that 115 is still within the population when you consider this IQ and the standard deviation of 50. Now, if I say a person has gotten an IQ of 145, not a person, I've taken another sample from the same population. Okay, so let's say this is sample B, and the mean of the sample is 105. What will be the Z value for this? If we use the Z score formula, this minus 100 divided by the population's standard deviation, you will get plus 3. Obviously, plus 3 is something way, way, way beyond 1.96. So you will confidently say that this is significantly different from our population. So usually our population is the null hypothesis. So when you're doing one sample t-test, your hypothesis is that the sample's mean is not different from the population's mean. So population's distribution becomes your null hypothesis distribution. And your alternate hypothesis is your mean, the sample's mean. So you'll have to place the alternate hypothesis distribution and see how and where it falls. So since plus 3 is in this rejection region, it is significantly different from our population. Right? Now, if I had used 0.01 in instead of 1.96, 0.01 means 99% effect or 99% confidence. So whatever we have as percentage in the acceptance region is the confidence percentage, right? So it is also the probability. If I take a sample randomly, 99% of the time it will be from this region, and 1% of the time it can be from here or here, as in 0.5% here, 0.5% here. That is what we say for 99% effect and 0.01 error or 1% error. Okay. So even if we take 99% confidence interval, so the acceptance region's limit becomes 2.58. So 99% cases lie between 2.58 and minus 2.58. So obviously plus 3 is way beyond that. So even in 99% confidence interval, this mean of sample B is significantly different from our population. I know it's quite a lot. Are you guys following? Is it clear? Questions, thoughts? Okay. So when we do this across both the sides, so we call it as a two-tailed test. Because you say 95% cases lie here to here. But sometimes we will know that whenever you're doing experiment, or whenever, usually in an experiment, you expect that depression scores will improve. You don't expect depression scores to, go bad. Right? As in depression scores of Beck's depression inventory will decrease if a person is improving. So obviously, you'll expect a person to improve, as in the depression scores will decrease. So you test how much it decreases. Okay, so that means from the mean it will decrease. So is the decrease significant enough, or is it usually within the population itself? Only if it is significant enough can you say that it is significantly different. In such cases, you use a one tail. If you want to decrease and you want to check for significance, you check on the left tail. If you're checking for significance of increase, you check it on the right tail. Right? So this is pretty much about hypothesis testing. But then again, there are a lot of errors that we can make because we are using standard error, and most of the time we do not know the actual standard deviation of population. So that is where a lot of errors will come up. We'll be talking about that much later. And there is also the errors are characters made. So some voice says, you think you solved it, but there are a lot of errors. So we'll be checking about errors of hypothesis testing and also power of hypothesis testing in the next class. Right? So did you guys understand today's class? Any doubts? Anything that you want me to recap? Alright, so those on YouTube, do let me know if you guys did understand, or if you want a different explanation, let me know in the chat. So we'll be continuing the errors of hypothesis testing in the next class, which is again tomorrow. So, the link to join the class and then WhatsApp groups and the link for the current class will be posted in the description.